All right, so I'd like to welcome John Bender from Sandia National Labs to give a talk about formal methods and verification.
Thank you, Professor. Let me get this hooked in here. Actually, let me take my glasses off first. All righty. All right, can everybody hear me okay? All right, excellent. Hopefully everybody can hear me online. If you can't, maybe raise your hand and someone will hopefully come to our rescue. My name's John Bender. I work at Sandia Labs. I graduated with my PhD from UCLA in Programming Languages and Systems in 2019. So it's nice to be back. I was sitting in those chairs not too long ago. So knowing that, I'll do my best to keep it interesting. So today's talk is going to be Introduction to Formal Methods, and I'll talk a lot about it. It's kind of focused. So the back half of the presentation is talking a little bit about our research at Sandia Labs as it pertains to the parts of the formal methods I'm going to introduce. Formal methods is a big field. So there's many different techniques, approaches to the goal of proving programs correct. And I'm just going to cover a kind of interesting subset of them. Make sure okay, hold on a second. There we go. Okay, so let's just talk about the problem in general. When you write programs, or you do basically systems on a computer, maybe they hardware or software, there's an enormous number of possible states, right? So just for Booleans, right? However many Booleans you have, there's 2 to the n of those, right? So you have n Boolean variables, you get 2 to the n states. For a little bit of context, if you take 8 32-bit integers, right? The number of possible states is something on the order of like 10 to the 77. So, and for reference, there's roughly 10 to the 80 atoms in the universe, right? So broadly speaking, naive methods for examining whether your program ends up in a bad state are just intractable, right? We can't go ahead and do that, right? So what is left for us to do? So thankfully, mathematics for a very long time has provided us the tools to do finite proofs for an infinitude of possible cases, right? So induction for the infinitude of primes, and simple stuff like the associativity for all possible addition of all possible integers for Ma's last theorem, right? So very, very simple to very complicated. We have this toolkit in mathematics to deal with enormous numbers of cases with small proofs. And with computers, luckily we have a very nice set of mathematical abstractions. In fact, like the whole purpose, the original thinking behind computing, right, is to give consistent results that we can abstract mathematically, right? And well, even though it's kind of, reifies as like a physical system, right? You get a processor that runs things, there's electrons involved and things like that. The mathematical abstraction is fairly tight. But even if it isn't, sometimes, we can have abstractions in computer science that are a little bit farther away from the thing they're modeling. We'll talk a little bit about specific examples of this later, but that's also fine. So even if in the case of your model of the computing that you're doing, even if it's kind of farther away, it's more abstract than what we're used to, ones and zeros, binary, you can still get good results out of it. So an analogy for this is gravitational lensing. So, and you can get results not unlike this, not quite as exciting, but gravitational lensing was predicted in the late 20s by the theory of general relativity, right? So some folks took Einstein's equations, poked them, prodded them a tad, and they came out with this idea that light should bend around really large bodies like stars. But they didn't have any way to verify this experimentally. So they had a model, their model of the universe was very disconnected from the physical universe, right? It's mathematical equations and physics is the rest of the universe. And much later, in the late 70s, they figured out a way to do this experimentally with the telescope technology at the time, and they were able to verify that what the model predicted about the thing it was modeling, the physical universe, was actually true, right? That light really does bend around heavy objects. The picture here is from, I believe, the Hubble, though that was obviously much later. But they were able to observe it in the late 70s, I believe, as a consequence of a eclipse. So it's okay, even though most of the time our models are very close to the hardware. It's actually fine if they're not very close to the hardware, because they can still provide value. And so we'll talk a little bit about something like this later. I just thought this was a nice connection. So we like to do these kinds of things, right? as scientists, computer scientists, we like to model our systems, and those models can be connected or disconnected, but they can still provide useful information about the thing we're modeling. So what is formal verification in this context? Let's take an example. So hopefully everybody who is attending this class has had some experience with state machines. Okay, good. So we have an example state machine here. It's a state machine that's modeling a vending machine, right? Okay, good. So just like with the universe, right, it's very disconnected. This state machine looks nothing at all like the vending machine it's modeling. Yes, we can all agree that that's the case. So the top edge going out of the wait state says we're going to collect some payment. You can ignore the select there for now. That's sort of a side condition. Once you've gotten a payment, you're in the paid state. Now you have two options. The user can either select some candy or some chips, or they can cancel, get the money back. And then if they have selected and end up back in the wait state, but if they have selected something, they'll end up back in the they'll end up in the selected state. And then out of the selected state, we go back to wait. We collect the money, we decrement the inventory, which is supposed to represent, like actually vending. And then we set the payment to 0. So very, very simple model, right? Okay. So there's nothing, this is not a super complicated thing, but we can already ask sort of interesting questions about it. And in particular, what we're concerned with in formal methods is properties of a universal character, right? So ostensibly, anybody who's ever written a program has run it once or twice before handing it in for the assignment or for whatever purpose they were writing it. You can test the program, right? But a test can only tell you a very small amount about the program's behavior, right? So only for the inputs that you give it and the output that you get can you know that it's working correctly, right? By contrast, formal methods are concerned with knowing it for a large set of the inputs, right? So properties of universal character. So something like always and never properties. So the kind of key examples that we see of this most of the time are safety properties. So that is, safety property is the system never does something bad. A good example of this is like if you have a pacemaker never stops making pace unless it runs out of battery or something like that, right? Okay. And then the second set of properties are liveness properties. So the system does something, eventually does something good, right? So these are the two kind of broad classes of things that we care about, but they're, this isn't all encompassing, they're just sort of the kind of characteristic set. So what is, in the context of our vending machine example, what does this look like? Well, we can come up with kind of 3 things here just off top of our heads. So it's things that should never happen in our vending machine. It should never be the case that when the cash changes, that is when we have a cash prime, it should be less than the old value of the cash, right? So we should always be, our internal representation of how much money we have in the vending machine should be monotonically increasing, right? Okay. Second one is, if we cancel, then, sorry, it's never the case that if we cancel, the cash changes, right? Okay, so we don't want to collect money from anybody if they hit the cancel button, right? Okay. Then finally, one thing we might like to do is that we'd like to say that the vending machine eventually will make us money, right? Okay, cool. So let's look at that one in particular a little closer. So it's not actually the case that the vending machine will eventually make us money. Now, as far as the state machine is concerned, we can state this a different way and say that it's possible to make money, right? But what we said here is that eventually we will make money, right? And that's not guaranteed. People may arrive at your vending machine and decide they don't like broccoli chips and candy corn or whatever you have. Okay, so that's like that's sort of a taste of what formal methods looks like in terms of model and systems. So okay, so this isn't free lunch. So like I said, a lot of times what we do is testing, right? But these are properties of universal character. So the question might be like, well, why would I ever do testing if I could just do, prove properties of universal character about my systems? So it obviously has some limitations. I'm going to give you an example, and the example is going to be in terms of COMCERT, which is a compiler, a formally verified C compiler. It is a compiler that has been proven correct with respect to a formal specification of the C language and a formal specification of a target architecture. So one of the key limitations of formal methods is specification. Sometimes it's really hard to say what it means when your program is, what it means for your program to be correct, right? As an example, for COMCERT, there's a whole dissertation on how to specify what it means for a compiler pass to be correct. What does it mean for a compiler to be correct? And it's a treatise on the ways in which we can write down theorems of correctness for program transformations, which is what a compiler does. So specification can be quite difficult. A lot of times it's high effort. So these are mathematical proofs. If you've had experience with mathematical proofs, depending on the proof, it may be very difficult. It requires some deep insight into what's going on. Broadly speaking, these types of proofs, the proofs we do in formal methods in programming languages and systems, tend to be sort of broad but shallow. By contrast, in mathematics, they tend to be sort of maybe narrow and deep, right? I don't know if that's an uncharitable characterization of mathematical proofs. I tend to think those are the cooler kinds of proofs, but it just takes a lot of effort. There's a lot of proof work to be done, and not a lot of it takes a lot of deep insight, but it does require some insight. So it just takes a lot of work. At ComCert, for example, it's something on the order of 100,000 lines of the programming language which it's built, the proof, and it took something like, it's up to, I think, at least 2 decades worth of person years of effort. So it's a hard thing to do, a lot of effort. And then finally, there's some notion about like, well, I did my proof, like how do I know that the proof is correct, right? On pencil and paper, people make errors all the time. We have lots of tools that you can mechanize the checking of the proof, but then you have your trusted computing base, as they say, is expanded to include the thing that's checking your proof. At least in the world of formal methods, it allows you to very directly point at the thing that you are trusting, right? So when we write something down as a theorem and we state a set of assumptions, we can say that those assumptions are part of the sort of trusted computing base. So for example, there's this nice paper that was put out recently where they just literally wrote down, here's all the things that you trust when you're trusting ComCert to give you a correct program. A little more broadly, well, okay, if we keep adding all these tools in to do formal methods, aren't things getting worse because we're adding more code, there could be more bugs? Vaguely, not accurately, but suppose that those tools are used independently, right? And there's some like probability that there's a bug in both things, right? It's the product of the 2 probabilities, which we would like to be, we expect to be smaller. Now, they're not likely to be independent because it's human beings using them, but that's the sort of mental model we have, I think, in terms of trust. Okay. So what do we do in these cases? So where is the sweet spot for these limitations? First, if you understand what your system is supposed to do, so we would like to have clear requirements for what the system is supposed to do. This can be really difficult, right? So if you're working at a startup and you're building a product, on the web, this is not for you, right? Because nobody has any idea what their product market fit is, right? Okay. You're going to be changing the product constantly. There are no clear requirements. You're just kind of moving forward, attempting to build something. That's not a good place to do it. Also, because it's so much effort, you really want something that's high consequence. So we're going to put a lot of time and money into this. Is there a lot of value that we're going to get out of it? And then finally, for trust, we would like to keep the trusted computing base as small as possible, right? And so we do this using foundational tooling, things that are built on small pieces of code like type checkers and stuff like we do in proof systems. An example that I like to reference is smart contracts on like Ethereum, right? Blockchain. So as a kind of maybe an exemplar of where this should be happening. So this is a website called Rect. It's basically a list of the biggest hacks for blockchain smart contracts. And if you just look at the top 3, it's over $1 billion. Okay, so high consequence. Most of the time the code is, I for a while during my PhD, I was doing audits for blockchain smart contracts. Most of the time the code is relatively small, even for custom ones. And the requirements should hopefully be fairly straightforward, right? So they're writing it down in code. Ostensibly, they have requirements that they want, and they're going to deploy it, and it's going to be done, right? So you don't iterate on smart contracts you put out, right? So this seems to fit the bill, right? Or should fit the bill. Notably, many of the projects on this list aren't even audited, let alone had any formal verification. So, and as a total aside, I think if you wanted evidence that most blockchain activity or smart contract activity was haphazard, or at worst, worse, even a scam, I think this might be it, right? That they're not taking the time to audit, or let alone do formal methods on them, even though they're a really nice sweet spot for it. Okay. So this is all to say that there are domains where this really does make sense in spite of these kind of limitations that I listed. So let's take a look at some example methods in formal methods. In particular, we'll talk about, I think, two things specifically here: model checking and program logics. For model checking, we can return to our vending machine example. So model checking is the process of checking properties over a finite state machine, even if it has infinite traces. So let's take a look at some examples. So we had these properties from before, right? So we can translate this never property into an always property by just pushing negation in and say, well, it should always be the case that cache is monotonically increasing, right? Okay, and then we can take our always and turn this into a modal operator. So this is temporal logic of actions. And so that block there is notation for always. Okay, so we state this about our machine. We say it's always the case that the cache is monotonically increasing. Okay, and so that should be true. Separately, we have the other one, which says if we push the negation in, if you cancel, then the cache should remain the same, right? Okay, good. And then again, we just change the always into the block operator. And then we can do the same thing with eventually. Eventually is a little bit different. You take the block operator and then the eventually operator. So it's the block and the diamond. So this says always eventually, which means that in every state, at some point, something will be true, right? Okay. And so what we know this is true. This is not necessarily the case because in a particular trace, the one that just loops around and always gets canceled where nobody buys anything, right? It will never be the case that someone actually buys anything, right? So there's just that one trace, that really unfortunate trace where you make absolutely no money from your vending machine. Okay, and then as an aside, for the model checking nerds who might be tuning in, you can actually write this in a separate logic. So there are logics that their models, the models of the logic are more slightly, not necessarily more expressive, it's slightly differently expressive, where you can actually express this. I won't go into detail here, but I can talk about it later if you all want. But you can express this property for model checking. But the kind of takeaway here is that you can write these down in a logic, and you can hand them to a model checker, and it will tell you that these things are true or not true, right? It might time out eventually, right? There's no guarantee it'll finish depending on the state machine and the number of states that you have. But for our vending machine here, surely it will terminate, right? So you can have models, and you have an automatic method for checking these properties. Okay, so separately, we have program logics, and this is a really enormous subfield of programming languages. And I'm just going to touch on kind of the sort of most popular form of program logic, which is the Hoare separation logic, named after Tony Hoare. These program logics take the form of a triple. And the triple says basically if this statement is true, so this is a statement, this is a judgment here, and it says if this is true, suppose P, then if the expression, suppose P for some environment, so like the values of the variables, right, for the program, suppose P is true of that environment of the values for the variables. Now I'm going to execute E, and then further suppose that that E executes to completion, that is, it terminates, then Q should hold. So if I've proven this triple is true, that's what that means. Suppose P, execute E, then Q will be true, where P and Q are predicates over the environment that E is operating in, like valuations of variables. So what's an example of this? Okay, so I have my program E here, my expression E is I'm incrementing X, right? And my precondition is if X is odd and I increment it, then X should be even. Okay, this is not a super controversial fact, but it's a good example, right? So that's what it looks like. We've taken the environment X, but our environment just has X in it. We said that that's odd, supposing that it's odd. We increment it with 1, and then now we can prove at the end that it's going to be even, right? That X in that environment is even. And you can do this over sequences of expressions in a program, which allows you to kind of modularly prove your program, right? So if I have some expressions E1 and E2, I prove something about them where the conclusion is R. I take that new thing R, and then I prove the conclusion Q out of it, right? Okay, so you can see how these get glued together. So that's the basic idea behind Hoare logic. So an extension of Hoare logic is separation logic, where before I was just talking about variables, right? And this is a sort of fine distinction. Hoare logic also talks about the heap, which is important for doing proofs about real actual programs. So we kind of extend our predicate language beyond variables and kind of basic statements about variables to include statements about the heap. So in this case, we have a location L1 points to some value N, just like, pointer into the heap. And then you have two predicates that can be set up and separate in conjunction, which basically says that they are regarding separate parts of the heap. They cannot coincide. So, well, what does this look like? So if I have two locations, one's pointing to N and 2 is pointing to M, and then I assign the value at 1 to 2, then they'll both be pointing to the value that was at 1. Does that make sense? So this is what the way your heap evolves. But you see the key is that it's saying that those two locations are separate in the heap. So the key kind of takeaway for this is you can do things like this, where what you do is you have a heap and you say there's this other part of the heap. So R, there's some extra part of the heap. It's off to the side. I don't care about it. I don't need to know about it. I'm just going to reason about my local part of the heap, which is really useful if you're trying to prove something about programming and you have a large, set of things going on. In particular, separation logic is really helpful for, like, a good example is, let's say you have a program that takes 2 arrays and does some computation on one part of the array and then ships it down to the other one, right? So there's the top array here, has some value M, and then it puts F of M into the bottom array, right? The idea is that it should just go along and do it element for element. It's like a map or a zip, right? Okay. Now suppose that they overlapped. In particular, suppose that the destination overlapped with the source, right? Well, now I'm not writing, my second computation isn't F of N, it's now F of M, right? Because I wrote F of M into the second location if there was an overlap. Does that make sense? Okay, so having these properties and doing proofs about programs is really important, because if you can't say these two things are separate in the heap, there are lots of programs you can't prove correct, right? Okay. So these program logics admit a lot of automation, which is really nice. So kind of a really nice example is Framacy. Framacy is a tool that's used to automate these kind of proofs of these triples. So remember the triple I had before, which was P, E, and Q, right? Well, this is what it looks like in the program. You write some annotations in, then you hand it the tool, and it attempts to prove it for you. Because in a lot of cases, you could just do basically symbolic manipulation to get the answer and see whether what you got out of symbolic manipulation comports with your post condition, which is Q. And then, before I go too far, and then of course we had the odd example down there below again. Okay. So in reference to Framacy, so this is used at, for example, Airbus for verifying avionics software, right? So I think this is I referenced blockchain just kind of obliquely, but these types of things are definitely being used. Model checking is also used. I should have referenced it, but model checking, for example, is used at Amazon. TLA is used at Amazon regularly. Model checking is used in Amazon, but among a great many other places. But these tools are used in industry for doing real programs on important properties for safety and for things like airplanes. Separately, you can automate a lot of this. So Framacy does automate a lot of the work, but I don't know if he's tuning in, but Todd Milstein, who's in our lab, the PLSE lab, they had a really nice paper not too long back where they were working on automating invariants for loops. So with our logics, like I said, a lot of what you can do, you can automate and straight line code. The hard part is when you get to a loop. You have to come up with an invariant that's true that also implies whatever you're trying to prove as a post condition for your procedure or your bunch of code. And that can be really difficult. And so they have some really good work on automating. This isn't actually the last in that line of work, but that's a very hard problem, and it's a very interesting problem that folks at UCLA are working on. So quite separately, you can do these programs, or you can do these proofs for programs manually. So what does this look like? So remember we talked about a specification. Here's a specification for summing over a sequence of numbers. We can write down the specification in a programming language. So we can say, okay, here's a very simple version of sum that's based on functional programming principles. If you've taken a programming language class, you will have seen fold, hopefully. So you basically fold over a sequence of integers, and you apply the add, and you get a sum at the end, right? Okay, so the nice property of this is that as long as you know what a fold does, it's fairly clear that this is correct, right? It's relatively simple, right? Okay, by contrast, this is also simple, relatively speaking, but it's much more complicated than the fold, right? Okay, so one thing we might do is we might say, okay, we have a specification in a high-level language, like our functional language here, and we want to prove that the implementation in C does the right thing with respect to some mapping between the types, right? Because C integers are not the same thing as just like abstract integers, right? Okay. And so what we do is we can write that down. Now you'll remember from before that we had pre and post conditions, the P and the Q, right, over an expression. That exists here as well. There's a lot more going on here, obviously, than before. But that's still the basic idea. So the first thing we do is we say, okay, so we have an input, which is a list of integers. Now the list of integers in C is more than just like a list, right? It's also a size, so we know what the limit is, right? Where to stop. And then on the right, you'll see my left, your right. You'll see that we connect those things. So we connect the parameters in the C, and then we have a pointer from A to an array of length size, right? So we have this connection between the functional version of the functional inputs and the inputs to the C. And then secondly, we say that the output should be tied to this definition sum, right? So you can see here where it says return sum, because remember sum is defined as that fold up here. Sorry, up here. With one caveat, right? The Z type in our functional language doesn't have like a wraparound, right? It just lets you go, right? It'll just keep taking up memory, okay? I mean, it has some limit based on the computer, but it's not the same thing as an integer type in C, right? Okay, so there's a mismatch there. But you'll see that there's a mapping down at the bottom. So it says Z to C int, right? And this is the last bit of bookkeeping. So it says, okay, we can take any set of integers you like and do the sum, but at the end, we have to make sure that if it wrapped around, that sum accounts for it, right? Okay. And so now we can do this proof. You can actually do this proof in a proof assistant. So this is a tool called VST. And VST will give you a foundational machine check proof that this is true, that these two things are related based on this specification here. So you would like to automate most of this using Framatcy, and you probably can automate most of it. But for more complicated programs, Framatcy will fall over. And so sometimes you need to do it manually, and this is one of the tools you can use to do that, VST. Okay. Finally, I just want to give it a shout out. I don't have time to go through this because it's so expansive, but type systems. You are familiar with type systems, almost certainly. I'm sure you've used C++ or Java. If you haven't, you've probably also used OCaml, Haskell, or Rust, just to name a few. Type systems are program logics. They're just sometimes sort of impoverished ones that you can easily automate, right? So if you've ever used a type system, which I'm sure you have, you've used formal methods. Okay, so that's the kind of overview, I would say, at this point. Okay, I think I'll pause. Is there anybody here who has a question before I launch into the Sandias stuff? Is it worth checking in with the folks online? Yeah?
Ask for questions.
Okay.
They can maybe put it in the chat.
Yeah, here I can. If anybody has questions, go ahead and post it. I've got the chat up here. Okay. I think I'm going to keep going. So I'll just leave this here for now. It's fine. If you do, just go ahead and post them in there. So I'm going to give a little overview about how we take some of these methods and apply them at Sandia. This is all research that I work on. But there are three main projects I'm going to talk about. The first one, so verified compilation. So remember I mentioned ComCert, the verified compiler for C. Well, we use that at Sandia. In particular, the reason we use it is that I think you've probably figured this out by now, but like if you do some reasoning about your program, so we've done all this formal method stuff, maybe you did some proof using Framatcy or you did some proof using VST, did a lot of work, it's time consuming. All of that may be invalidated by a compiler bug, right? Okay, so, and even if you're not doing a proof, if you're looking at your program and you're thinking, my program does this thing, and whatever mental model you have happens to be correct, that depends on the compiler maintaining that mental model, right? So a bug in the compiler can throw off whatever you're doing completely, right? And bugs in compilers are very real. There's this nice paper, it's kind of famous paper from John Rager called, built on a tool called CSmith. And what they did is they compared compiler outputs, and they found lots of bugs. Compilers tend to disagree a lot. And this is not on undefined behavior or implementation-defined behavior. These are actual bugs, right? So obviously, implementation-defined behavior, we might expect it to, vary because, well, it's dependent on the implementation. But these are real bugs, and so they can invalidate the important, whatever reasoning you've done for your, system that is very important or high consequence. So that's why we make use of ComCert. Again, ComCert was a really huge and time-consuming project. Again, many person years in the making. Critically, it only works for single-threaded programs. So, and that's great. Lots of programs are only single-threaded, so that's fine. But we've sort of moved, as a consequence of Moore's law kind of tailing off, we've moved into the sort of multi-core era, right? And we are interested in multi-core programs, so we would like those programs to be correct across the compilation process. So we're going to attempt to, what we're working on Sandias, we're attempting to extend it, which has been done before. So ComCert has been extended to admit concurrent programs. But the kind of key feature of all those attempts is that they required basically a major overhaul of the compiler, which is not super surprising, right? If you take a single-sided compiler and you prove that it's correct, and then you decide to add non-determinism, threads and all this other reasoning, the proofs become very different, very complicated. Intuitively, that's the case. So we're trying to avoid that because we take many upstream updates from ComCert, so we need those. So when there are features from the compiler, we bring them in. There can be optimization passes, new backends, et cetera. So, okay, so other people have tried to do this. What hope, I work on concurrency for what it's worth. This is a slight detour. So my expertise is in concurrency. So my PhD is on memory models and concurrency. Java's memory model in particular. And at first, that may be sort of, this might sound not related, but Java's memory model is explicitly intended to be very similar to C++'s, although it diverges in a few key ways. In particular, Java is not allowed to have undefined behavior. We updated this recently, so recent work with Jens Palsberg in the PLSE lab, who is my advisor, with Shuyang Liu. We fixed the volatile compilation in Java through our model. So you'll remember we talked about the lensing, right? Okay, so they looked at the model, they were like, wait, there's this weird thing, like light should be bending around stars, right? And then they went to go find that, right? Okay, cool. So we did the same thing. We modeled Java's concurrency as defined in their specification. We created a formal model. And then we actually got an email from somebody in the community who was like, hey, I looked at your model and there's this weird behavior that shouldn't, it portends a conflict in the specification, right? So it was internally conflicted. And we went and looked at it, like, oh, wow, that's true. So we had to fix the model, right? So in the same way, obviously that's not quite as exciting as gravitational lensing. But we looked at our model, found an interesting property of the thing we were modeling, and then we were able to correct it. So actually, it's still outstanding. But yes, Professor.
How do they find that bug in your model?
Great question. Excellent question. So these are very complicated axiomatic models. So the question is, well, how do you explore the model, right? Okay. So there's really amazing set of tools for memory models. If you can define them in this axiomatic way, you can actually take a strong model and relax it backwards towards your weaker model, and along the way find bad behavior. And so it can actually generate counterexample programs for you that violate some property. And so we actually had someone, and I'm not sure they actually did this, but someone came to us with a counterexample from the community, and we're like, hey, and we're like, wow, that's true. Let's go fix it. So, and that's in the acknowledgements here. I think you can even see it on the screen. But yeah, great question, right? It's kind of amazing. Like that's the whole idea. If we define it formally, now we have a mathematical object we can poke and prod in a systematic way so that we can find interesting properties about the thing we're modeling. And in this case, we found a real bug for compilation power. And on top of that, it also forced an enormous amount of amazing work by the lead author here, Xiang. She spent an enormous amount of time actually writing down what it means for Java's volatiles to be compiled. We had to talk to Doug Lee, who basically maintains Java util concurrent. We had to ask him, are these optimizations in the compiler, are they valid relative to like C++? And he gave us lots of answers. And so we built our knowledge of the model. The model became more robust. There's an enormous amount of proof work in here that she did to prove that it was correct and the compilation was correct. So this is a really amazing kind of piece of work that kind of fell out of this idea of modeling a real system. Okay, so this is an enormous detour, but I think it illustrates the point, which is that your compiler can have bugs and really nefarious ones if you're not very careful. And so we probably should be verifying these things, right? And we would like our programs that we've done complicated reasoning on to go through a compiler that preserves that reasoning, right? So there's lots of very good reasons to do this. Okay, so why is it that we think that we can do this? So there's this nice paper from very recently It was in Popple, where they were able to model the interaction between linked code, so calls to external procedures in C code, using game semantics, which is, if you're pattern matching on game theory, it's not totally wrong, but it's not quite the same thing. But what it does is it models interactions between an actor and its environment. And those interactions are modeled as like moves in a game. And so they were able to do this, and the key property of it is this table here. So the whole paper, if you read only one part of the entire paper, this is the part you would have to read. And it's this table, which basically says they added this proof for compositional correctness with respect to externally linked code, so externally called procedures, and it altered only 3% of the proof code, which is sort of amazing. If you think about these, the proof of a compiler is a very complicated and delicate thing, and they were able to do it by making a small tweak in reasoning about it, right? So, okay, so you may say to yourself, okay, John, that's external procedures. Why is it you think that has anything to do with concurrency? Well, it's related, at least. You can think of, if you're doing well-synchronized code, it's actually not totally unreasonable to think of releasing a lock, like calling an external procedure where you let the other parts of the program run. So that's not totally unreasonable. You can model it that way. Concurrent C is not that. It's actually much more complicated. But I think the basic premise holds. You get a set of moves between you and the outside world. So basically the thread you're compiling currently and the possible set of other threads that you've created. You model those interactions using the memory model. And then basically you do the same thing that they did here. And then you build a kind of basically a linking proof at the end, where you're not actually linking code, but you're rather composing threads. So that's one piece. And then separately, there's this nice paper where they have a nice model of C, the C memory model as event structures, which are the underlying mathematical object in game semantics. So that's kind of our approach at present there. There's also a lot of other side conditions and things we have to deal with. So just first and foremost, the proofs in ComCert for single-threaded programs assume determinism. So once you factor out external calls as observable behavior, C is deterministic, right? So if I'm doing my proof, I say, given a set of interactions with the environment that will happen for both programs, now C and its child languages that it compiles to will behave deterministically. So that the whole proof structure is based on, it hinges actually on determinism. So we have to deal with that first and foremost. But you can already, you probably already sort of heard the answer to that which is to factor out the non-determinism in some sense or another, right? So this is something we're working on now. This is a kind of a long-term project. It's delicate, I would say. Okay, totally separately. This is yet another detour, but this is a separate project. Going back into space yet again. If you put a processor in space, radiation will often ruin your computation. It will flip bits, right? So there are lots of solutions. People have been thinking about this for a very long time. There are lots of solutions for how to deal with this. A natural one, upfront, natural one is, let's have two processors, and we'll set them a little farther apart so that, if a beam hits one of them, it won't hit the other one. It has a low probability of hitting the other one. And we'll compare their answers. If their answers don't disagree, we start over and do that part of the computation again, right? That's called dual modular redundancy. You can do it with more than one processor, right? There's lots of other solutions like this. The key kind of thing that most of them don't address, though, that we do care about at Sandia is supply chain trust. So you can think of transient faults, that is radiation-induced faults in your processing, like a trust problem. Only it's not nearly as bad because it's probabilistic, right? Whereas if you have a bad actor who's providing you a processor, that can be clever, right? That could include clever reasoning. It's not probabilistic; it can be deterministic, and so it can do clever things. So, for example, if you had two processors sitting next to each other doing the same computation, and they were both similarly nefarious, they would agree on their nefarious computation, right? Okay. So to address kind of these issues generally, we take a heterogeneous approach where we have a very fast processor and a bunch of kind of slower trusted processors. So it is often the case that the processor that you can make for yourself or that you trust is going to be a little bit slower. So that represents a problem, because if they're both really fast, well, then you wouldn't need the other one. You just go with the trusted one in the first place, right? But think of what is the name of the probe on Mars? Is it Perseverance? Now, one of them. Anyway, it has a very old processor in it. Like it's a very old processor, extremely large features, and it's hardened. But as a consequence of it being very old, very large features, large transistors, it's very slow, right? So the thing you would like to be able to do is to have fast features, have a fast processor, maybe that you don't trust as much either because of radiation or for supply chain reasons, and then have your slow processor kind of check it, right? Okay, so that's the basic idea here. So this is a bit of example code here. I'm gonna get rid of the chat there. So a bit of example code here, and it's just a computation. There's nothing super interesting about the code, but the key thing is it's doing, it has some dependencies, right? Okay. So if I want to run this code and have it checked somewhere else, one thing that you might want to do is to parallelize it, right? So we'd like to parallelize the checking in some sense, because if I could have a ton of slow processors I trust, and I could somehow parallelize my computation, then maybe I could catch up with the fast processor. So I'd get a fast computation that gets checked by a bunch of slower trusted processors. So, but the key kind of problem with this is dependencies in your code, right? That makes it very hard to parallelize that, right? To divide and conquer, right? Okay. So the key insight here for this project is simply that when the fast processor is running, it resolves dependencies for you. Okay, so let's look at an example. So suppose we're executing this code, and on the one side we have the executor, and the other side we have some checkers. Okay, and the kind of the larger box there is meant to represent a faster processor visually. Okay, so we start out, and let's say, for example, that m in this case is 0, right? So it came in as 0. Now, first thing that's going to happen is the executor is going to finish first because it's faster, right? Nominally. Well, when it finished, one thing that we must have noticed is that the dependency on x for the next computation has now been resolved, right? So you know what the value is supposed to be for that x for the next computation. So we can substitute that in, and then go off and in parallel do the next computation. Now, you may be thinking to yourself, how do we trust the 2, right? If we just got it from, we got it from the untrusted executor. Well, we don't trust it, right? Remember, we're still checking the first computation, right, on another parallel checker. So we have both of those checkers running. And if the other one comes back and says the 2 is wrong, then we stop what we're doing and we go back, right, and we try again. Does that make sense? So you can do this. And the nice thing about this at this kind of tight level, at the instruction level, is that you can do the checker can have a very wide pipeline, right? Because the thing that's going to start a pipeline is dependencies, right? So you can just spray a bunch of a very wide pipeline in your processor, spray instructions out across them, and you get a highly parallel set of checking running very quickly, even though your execution unit can actually be kind of slow, right? So it's very parallel processing. So that's one way. Now there's a second way that we can also do this. So, and I should say that this basic idea of having a checker kind of welded into the pipeline of the dynamic processor appears in this paper about DIVA, and the kind of idea of having the wide pipeline is innovative work that some of my colleagues have been doing at Sandias. There's a second way that we can resolve dependencies using the executor, right? So same idea, but the executor, as it goes along, can act as a perfect branch predictor, right? And a thing you may hear kind of in, kind of a folklore, I don't think this is necessarily true all the time, but people will say a lot of modern processors are devoted to branch prediction, right? So what we can do is we can allow the executor to do the branch prediction for us, and we will record its selections and check them. And then what we can do is linearize the code, and since it's doing the branch prediction, we can linearize the code. And then once it's linearized, we can just take that linear string of instructions, partition it, and check it in parallel as well. Right? Okay. So that's the basic idea behind this project. That's like the key motivating insight. So I just talked a whole bunch about processors and kind of optimization. And so a natural question we have is, what does this have to do with formal methods? Well, of course, I proposed this project and I've been working on it because I'm actually not at all interested in heterogeneous computing. That's not strictly true. But my main bent is to get back to questions of correctness. So this presents two particularly interesting. where the branch prediction is concerned, presents two particularly interesting verification problems, and we'll state them as theorems. So the first one is if I've given a program, so just as to go back here for a bit of context, to do the branch prediction, once I get to a branch and I've decided where I'm going, I have to record that value so later I can do the linearization, right? Okay, so part of it is I have to instrument my program. That has to happen, otherwise I can't do this, right? So if in particular, if I'm doing it in software, if I'm doing it in hardware, I don't necessarily need to instrument it, but I want to attempt this in software first. So first I need to verify that when I'm instrumenting my program, I don't break it, right? So just like a compiler, when I'm proving a compiler correct, I make some transformation to the program, and I want to make sure it doesn't violate the semantics of the program, right? The behavior of the program. In the same way, I don't want my instrumentation to break my program, right? I want this to be a general approach. So given a program P and an instrumentation path, I'll call F. F applied to P is simulated by the original program P. So the word simulation has no meaning yet because I haven't defined it. But basically what it means, intuitively what it means is the behavior of the instrumented program is smaller. The set of behaviors of the instrumented program is smaller than the set of the original program. That is, my instrumentation pass is not going to introduce new traces or new behaviors into the program. That's what it's saying. That's what simulation means in this context. It's a very overloaded term, I think, in general, but that is the sort of term of art in formal methods. And this is the same with compilers, right? My compiler should not introduce new behavior, right? For every, and the sort of simple version of this is, for every behavior in my instrumented program, there should be a corresponding behavior in the parent program, right, the original, right? That guarantees that anything I do in the instrumented program is covered by what was done in the original program. Does that make sense? That's called backward simulation. So this is one theorem we'd like to have. Basically, at a high level, this says the instrumentation doesn't break P, right? Okay. So that's one proof I'd like to have. I don't want my instrumentation should be verified. And as an aside, maybe this is just sort of like a curiosity, but if I'm going to do this in software, the hardware people want guarantees. So hardware people like guarantees. They do a lot of work doing formal verification because it's very expensive. If you ship out a piece of hardware, you can't correct it later necessarily, right? Microcode excluded. So what we want to do is give a similar sort of guarantee if we were to do this type of instrumentation in software. So that's why we're doing these types of proofs. Okay, so a second theorem that we would also like is given a program and an instrumentation pass and an execution of the instrumented program where the execution is basically a relationship between states, right? So I go from one state, I take some steps, I do some computation, I end up in some other state. Where P is the program, S is like state, like variables of memory, and I is some values of the instrumentation. So in implementation, S and I will be obviously kind of overlapping, right? Because we'll be instrumenting it into memory, but for formalism's sake, we can separate them. Then if I linearize the code up to using the information I got from instrumentation, right? I linearize the code here, then I should still end up in the same state, right? So the key, this basically says that my instrumentation pass is going to give me the linearization information, or the instrumented information is going to give me the correct linearization so that I end up in the same state, right? So the key thing I said here is if we have a perfect branch predictor, I can get a linear stream of instructions, right? As long as I have a perfect branch predictor. That depends on instrumenting it so I get the branch prediction information, right? So now the proof I want is if I linearize my code, I shouldn't linearize it in a way that changes the behavior of the program, right? That's key. And then what I can do is I can take that and I can use that. So has it given up entirely? Okay. It's just taking its time. Okay. So intuitively, again, this means it's up there, but it's not here. Can anybody, it seems to have paused here. I'm not sure. It's working here, but it seems to have disconnected. Let me try this real quick. Meeting disconnected. Well, that would do it. Try clicking the link again.
Got a network problem?
Seems that way.
Yeah. So the meeting is still there.
Yep. Yeah, it's just my laptop seems to be disconnected.
So you are on Wi-Fi.
Yep. Let me see if I can. Imagine we'll sort this out. There we go. Okay. Yeah, we'll see here in a second. I'm still,
I think you ran into the Zoom 40-minute limit, something like that.
might have been, yeah.
The thing that's 40-minute limit. It makes no sense at all.
Okay, let me share my screen. Okay, I dare say we're in business here. Let me see if it updates. Does indeed. That's good news. Okay. Okay, so theorem 2 basically says, as I was saying, linearization doesn't break the instrumented code, right? So we showed that instrumentation doesn't break the original program. Now we want to show that linearization doesn't break the instrumented code, right? And the key property is that when we linearize it based on the perfect branch prediction, it's going to take out a bunch of, instructions and conditions, right? We're going to take a bunch of things that would otherwise have been jumps and turn them into just straight line code. So it's very important that that is not broken code, right? We still want it to be executing the same thing. Otherwise, we're not doing checking anything, right? Which was the original goal. Okay, so what does this mean? Well, it means that if the executor is executing the original program and it takes 3 steps, or it takes 2 steps basically, or a set of steps between the next 2 states. So P1, P2, and P3 along with their attendant states. Then we can do the checker using the linearization of the first step and a second checker using the linearization of the second step, right? So these are the sort of, and to be fair, these should be propositions. We haven't proved these yet for the past. But these are the sort of enabling theorems so that we know, and they should be proven for actual programs, actual passes in a compiler, so that we know that our linearization is correct. So this is the formal methods inside this project, right? And this was actually my main motivation, sort of getting in trouble with these sorts of things outside my sort of wheelhouse. Okay, and the last one. So remember we talked about the vending machine here. So one thing we said was sometimes we can poke our models, and the models will say something's wrong, and then you can go look at the thing you're modeling, and you can say, oh, okay, the problems exist there as well. That's good. We learned something about the thing we're modeling, and that's, either we fix the thing in the case of the Java compiler, or we say wow about the universe because we can't fix the universe. But separately, what if our model says everything's fine, right? So we have a bunch of properties for our model, and all those things, they all are correct for the model, but then we have the thing we're modeling. There's an open question now, right? Which is, what if the thing we're modeling just behaves differently, and the model is just totally disconnected from reality, right? Okay, so in science, what this looks like is you observe as many things as you possibly can. You gather as much empirical evidence as you can to gain confidence, right? But in computers, these are all abstractions of, nominally pretty mathematical objects. So in theory, we should be able to tie our model relatively tightly to the actual implementation. Okay. So what we'd like to do is tie it to like a C program. So this is a somewhat contrived C program. It looks a little bit like, what you would write if you were writing a vending machine. It's simplified for obvious reasons. But the question is, how do we make a connection between these two things? And there's a fairly straightforward way to do this. But the first thing to do is to observe that each chunk of code corresponds with an observable behavior of the vending machine. So we're going to do stuff in our code. Sometimes it's not going to correspond with something in the vending machine, right? There could be extra bookkeeping, but somewhere along the way, it should have the same observable behaviors as the vending machine, right? So in this case, let's just say for the sake of discussion here, that the vending machine, the observable behaviors of the vending machine are anything you see on the edges is defined here. So just, we'll make it totally expansive. So the C program should exhibit them in some way, shape, or form. So we need a couple of things. One, we need to say like, well, wait, how do these two things correspond, right? So this is pretty simple in this case. Payment corresponds with payment. Select corresponds with select. But they need not, right? You can have different, very complicated data structures in C representing relatively simple things in a state machine, right? So you have basically a relational mapping. This is called a simulation relation. And then secondly, we have to demonstrate that the C produces in the same way the observable behaviors of the vending machine. So here in this case, the two things that are being pointed out, you can see that the payment's being set and the select is being set to null. So the mapping between null and the C program here is 0. Secondly, we're reading a selection, be that cancel, select, or candy and chips, cancel or candy and chips. Third, there's a possibility of canceling and continuing. And then finally, there's the payment. Now, very critically here, if you're watching very closely, right? If you look on the right, you may stare at this a second and be like, okay, that seems fine, right? Because it's kind of lexically ordered correctly. But the behavior of the state machine is actually different than the program. And this is not be immediately obvious why, but look at the program for a second, ignore the state machine. It's first setting the payment equal to 0, so it's knowing out the payment before it's recording the payment as part of the cash, right? Total cash on hand. Okay, that's obviously a bug. So the question is, well, wait, how did we catch that? Like, how would that get caught, right? Okay, so let's look into this a little bit more closely. So first thing to recognize is what we're gonna do is we're gonna say the starting state at the beginning of this kind of transition as it exists in the vending machine and as it exists in the C code, those starting states should be the same. So the cash on one hand and the cash on the other should be the same, right? So the starting state here is the non-prime variable in the vending machine, and the cash 0 is an initial state, right? Because remember in the C, we don't have a single state, we have a couple states as we go through each of the expressions. Then for each of after each of those assignments, we get new versions of the variables that we're going to track the state in. So for payment, it's the next value, the next state of payment, payment 1 is 0. The next state of cash, cash 1 is cash 0 plus the payment you just assigned. And then finally, we're going to say, well, okay, the final state should be the same as the one in the vending machine, right? So cash prime should be equal to the final state that we have in C, which is cash 1, right? And now this becomes a satisfiability problem, okay? And we can say, all right, is there any assignment to these variables where cash prime, which is the thing in the vending machine, is different than cash plus payment, which is what we expect in the C code? And is there any assignment to the variables that makes payment prime not equal to 0? So in the case of payment prime, doesn't matter what order you do this in, it's always going to be 0 at the end, right? So that we don't have to worry about. But for cash, we do. So we look at this very closely. We see, well, if we do some substitution, we can take cash prime is equal to cash 1 according to our final predicate there. The last one in the state below cash plus equals payment in the C code. And then we do a further substitution where cash 1 equals cash 0 plus payment. And now the question is there any assignment to these variables that makes them different, not equal, right? And then it's whatever you want, right? Because we blew away the payment, right? So any value you like for payment 0 will make these different. Okay. Now, a natural question is, what will it work if you fix this? And the answer is fairly straightforward. So if we flop those to be correct, right? So we record how much money was in the machine, and then we zero out the payment. The key thing that changes here is that now cash 1 is equal to cash 0 plus payment 0, not payment 1, right? So that then when we do the assignment down here, there's no assignment that's going to differentiate these, right? Okay, so this isn't actually what we do. It's just easier to explain. What we actually do is we do this as pre and post conditions, and we allow the kind of internal machinations of FRAMC, which sometimes shells out to things like, a SAT solver or Z3 to do the work for us. And sometimes it involves ghost state. But the basic idea is the same. So what we do is we make sure that given some assumptions about the states are correct at each of the steps in the vending machine and in the C code. So starting with the precondition saying they're the same. We record how it behaves in C, and then we check to make sure that that works for the single kind of one-shot behavior of the vending machine model, right? So this is just a subtlety of the difference between state machine semantics and C semantics, right? Because the state machine does everything in one shot. It basically takes its and does everything in parallel with its starting state and comes up with an end state. Whereas in C, everything's done in sequence. So there are cases where you can screw this up. So you have to make sure that whatever you do to get this correct, you account for it in bookkeeping. Okay, that's the key insight there. Quite separately, we also have a notion of refinement, that is moving the state machine closer to C when the implementation is something you want to specify more closely. So this is not something you normally encounter in even I think in graduate studies. I mean, suppose of where you're getting your graduate studies with respect to state machines. You can extend the state machine in a couple of ways. There's two types of composition that are kind of broadly recognized, I think, in the literature. One is parallel composition. So you can run two state machines next to each other. They can have shared variables and do different things. That vaguely maps to concurrency, right? So something like that. Separately, what you can do is you can nest state machines. It's not the same as, but you can kind of get a flavor for it like it's calling a procedure, right? So one way you can think about this is, okay, I have my high-level model of vending machine. I have some properties that I proved about it. I like that. I don't want to change it. In fact, I don't want to change the observable behaviors at all either. But I do want to say something about the implementation, maybe about low-level details that the person writing the C program has to adhere to. So what I can do is I can refine each of these states by saying some stuff goes on in this paid state, right? So like, for example, when you're selecting something in a vending machine, it's often the case that you press a few buttons, and that's the thing that gets you the candy, or you press some other buttons, and that's the thing that gets you the chips, right? So you may want to say, here are the buttons I want to be pressed in the case where I get the candy or the chips, right? And so you can enforce that down into your C model by putting it at the high level without actually modifying the original properties of the higher level model that you wrote originally, right? So you can refine it structurally towards the C for these purposes. So this is something we built in as well. Another way to think about this is you can think about it as extending the behavior between the paid and selected states, right? I have a behavior that at the end says I selected candy or chips. But prior to that, there are a whole bunch of stuff that goes on before it, which is not observable, right? So this is just like a compiler. When you write a program that prints out hello world, right? There are a lot of things that go on between that, like one-liner you wrote in, Python, or I guess it's not a one-liner in C, but pretty close to, whatever, a one-liner in C. There's a lot that happens in the program that has nothing to do with printing the standard out, right? The compiler adds a bunch of bookkeeping in there, right? Nominally, right? So, but that's fine because it's still the same program because the observable behavior is the same. This is a very similar idea, right? What we're doing is we're tacking on non-observable behaviors for the purposes of refining our implementation down towards what the actual implementation is in C. So that's what this is useful. Yes, Akshay, what's up?
So do you generate the refinement automatically?
So good question. So this is sort of the key property here. So you may be asking one or two questions. I'll try and answer both. The first question you might be asking, which is the nesting a refinement automatically? That's a matter of the semantics. That's just like a theorem or just like a property of semantics. Well, the other question you're probably asking is, do the predicates, the pre and post conditions that we insert and have proven by FRAMC or whatever we do manually, does that imply refinement from the state machine down to the C? And the answer is yes, that's the whole goal. Because if it's a refinement, and I'm glad you asked the question because it's reminding me, because if it's a refinement, then all the properties that are true of the state machine are also true of the C program up to the simulation relation, right? So we have some mapping. Obviously, if you screw up the mapping, that's not good, right? That won't work, and you could get a proof nominally. But hopefully, what you have is a mapping that's fairly boring between like some basic values. You're kind of mapping states to code points and things like that, right? So the mapping should be very boring. That's what you'd hope for. That's where this nesting can help. But yes, ultimately, what you want is a You want a theorem, a high-level theorem that says, if we set up our program this way, and we get a proof out of pharmacy or VST or whatever, then the C code is a refinement of the state machine, and thus all of the safety properties that are true of our state machine hold for the C. Right? The correctness properties, safety in particular, not liveness, if it's a refinement, if it's a strict refinement, are carried along that refinement down to the C. That's the whole idea. Yeah.
I'm a little puzzled about the causality here.
Yeah.
That is, you have like conditions attached to these preconditions that are scattered throughout there. So
Yes.
does one think of the refinement as being like a subroutine, and a precondition at the top level sort of causes a precondition at the refinement, or is it the other way around? Is this high-level machine sort of an abstraction of the low-level machine, and any precondition of the low-level machine sort of maps into a precondition of the abstraction?
Well, so the preconditions in this case, so just as a matter of clarification, this may not be the question you're asking, but as a matter of clarification, the preconditions here are purely for the sake of establishing the refinement. So we basically say, I mean, you can say lots of things about the C that you want as an aside, but we basically say nothing about the C other than there's a mapping between the states and the state machine. We basically always talk about the state machine. We use model checking to say all our properties are true of the state machine, and then those travel down to the C. Yeah, the preconditions are purely there to establish that refinement. Yes, that's a good question. So yeah, so this is a project that's been going on long before I was at Sandias as well. This is actually a very cool thing. It's actually the case that this idea, state machines have been around for specification of correctness of programs for a very long time, right? Okay. Leslie Lamport has a Turing Award, and a not insignificant part of that was TLA, right? So like this is a well-trodden ground, but the connection to actual programs is is hard. It's very difficult, right? And so the program has to look a certain way, et cetera. But there's not a lot of work in doing this. I mean, even TLA has this like pseudo programming language, which is kind of compiled into a spec. It's not actually a programming language. And I think even at Amazon, they don't connect it to the implementation. It's very much a disconnected model, right? But what we're doing here is we're saying, well, we want to connect them together. And there is work doing this, but a lot of the current work is very onerous. You end up with multiple levels of specification definition, and you have to do very difficult simulation proofs to connect your levels of specification together to get down to the code. So I think the limitation here, because this is not a free lunch, it never is. The limitation here is largely that the program has to look a particular way, right? So you're limited, you can't have loops, and you can't necessarily have loops. You can work around having loops by adding invariants and manually intervening. But if you have loops in one of your transitions here, you have to guarantee that they terminate, right? And then even then the reasoning is difficult, right? Because if it divergence is an observable behavior, right? So if my C implementation just spins off on a loop, that's obviously not, I mean, it could be in the state machine, but it's not going to be across a single transition. So there are hard limitations of what you can do here, but it satisfies quite a lot of, it provides a lot of value in the context in which we use it. So yeah, this is quite good. Okay, I think that's pretty much it. Yeah, that is it. I think we're an hour and 15, so I think I'm at my limit anyway. Are there any questions here before I call it a day? Okay.
Can I ask a dumb question? So
Please.
There's this paper in the systems world called Cores That Don't Count, published by Google. I don't know if you've seen it, in which they basically found that there's a bunch of CPUs out there and their enormous server farms that are flaky. And it's usually one core that's kind of flaky, and what they're measured is that CPU reliability has gone down in the last 5 years or so. I'm wondering if there's some way that the work that you're doing can help out those folks.
So yeah, it would be great. So this would be very cool. So here's what I'll say. First and foremost, the thing that must be said is our preliminary results show that it's dependent on how fast the more reliable thing is. And it often requires many such cores to keep up. So you're trading a lot of energy and potentially heat to keep up. And the speed up it's not like a linear relationship, right? Okay, so that's the first thing that should be said. Second thing is, there's actually already a lot of literature in catching these kinds of things, because people have been predicting this for forever. They thought, oh, as we get down to, they were predicting this at like the 20, 30 nanometer level, and we're way past that now. So I think there's a lot of better research in just detecting those kinds of local transient faults that I'm sure that they're aware of. This is very much aimed at the context in which we need to know for sure that we're getting the right computation, right? It can't be like probabilistic. There's none of like we can.
You worry much more about supply chain stuff.
Well, yes, it addresses that. Initially, we were actually mostly concerned with radiation difficulties, but it just turns out that this approach is very good for trust, and trusted computing has become a big thing because of supply chain attacks and things like that, right? So, and there's lots of other work in this. There's obviously probabilistically checkable proofs, although the kind of the verifier work in that it's still a long way from being sort of practical. But in the sense that the verifier actually has to be trusted, this can actually augment that because you would need a trusted verifier, and you would like the verifier to go fast because it still is computationally currently very difficult, right? You need as much speed as you can get. So this can actually augment that as well. But anyway, this is all to say that there's lots of other research in this kind of space. I don't know if this will help them. It'd be great if it did, but yeah, I don't know. All right. I checked. I pulled up the chat. Is there anybody? Yeah, if there's anybody in the chat who has a question, please feel free to ask. I haven't seen it, so I imagine they're doing the same thing I did in 201. I've written my summary, and I'm going to go have dinner. Anyway, thank you all very much. Thanks for everybody in the chat.